Thank you. Well, you're good. How are you? Good. Okay. So you're on the.
Nobody. I said nobody.
And the people who are online here, hmm, Supriyo, can you hear?
Yes, sorry, I could. I just declared it chat. Thank you.
We can hear you well, Art.
Try again. 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 I'm gonna call Supriyo and see if he can hear me.
I can also hear you.
I'm not sure I can hear him.
Can you hear me, Art? I can hear you.
Okay, but I'm not sure I can hear you. Can you try saying something? I see. Okay, I'm just trying to figure out if I can hear people when they talk. Okay. Okay. And if you're there, can you say something? I can't tell if I'm getting audio from people who are online.
Art, this is Ann.
Says she's talking,
Yeah.
so we're missing audio.
Okay.
Okay, let's ask someone a tough question and have them answer. One of your attendees.
Anne, can you try again saying something?
Oh, she might be muted. Everyone's muted. You have to unmute too.
But I think she was able to unmute herself before.
That's the free.
Supriya, can you try saying something again?
Supriya's muted.
Can
Oh,
can you hear me?
Yeah,
yes.
Okay,
okay, thanks.
I'll be there.
All right. I think we have the technical problem solved, or at least the beginning. So welcome to NMR spectroscopy of macromolecules. Hopefully there won't be 10 minutes of difficulty every class. We'll try to work it down minute by minute in each class. Normally on Wednesdays, after the lecture, we'll have problem sessions, but we won't today because we're recruiting faculty at Columbia and have to get back and interview prospective faculty members. I also think that you probably don't yet have access to the Dropbox folder where the course materials will be put. So hopefully everybody has emailed Whitney, and we'll get that set up, and I'll have the lecture notes will be posted there. Zoom recordings will be posted there, problem sets, etc. There's 3 lecturers this year. So Ann McDermott is online right now. She and I have been teaching this course almost 30 years, Ann. And Hashim al-Hashimi will join us this year, particularly to talk about applications to RNA. Well, let's see if we're going to be able to advance. There we go. The material, at least in many aspects of the course, is taken from 2 books, Protein NMR Spectroscopy and Multidimensional Solid State NMR. Must have the title wrong. It's either of, should be probably of polymers, but neither of them are really required. And there's loads of review articles, et cetera, that you can use to help fill in gaps. Of course, if you actually buy a copy of this book, I make about $1, so I'm always happy about that. So today, just to start getting used to some of the language that we'll use over and over again. Hopefully for a lot of you, this is just review. We want to make sure we're on the same page and no one's confused. For the people from Hashim's group, this is a protein, one-dimensional protein NMR spectrum. And the things to notice, of course, are there's first some chemical information. The backbone amide hydrogens in a protein tend to resonate in a region centered around 8 or 8.3 parts per million. You can see there's another band where the aromatic hydrogens are, the H alphas, the other aliphatics, and then most upfield, the methyls. So there's chemical information, of course, in the spectrum. And then within each band, there's some degree of dispersion caused by in the protein by local, secondary, tertiary quaternary interactions. If we denatured this protein in urea or guanidinium, we would see a great deal of collapse of this dispersion into this kind of a lot of overlapping resonances. So there's information about structure in the dispersion, and part of the course is try to understand how we get information about structure and dynamics out of the properties of the NMR spectrum. You can also look over here at these two upfield peaks, and clearly they have different line widths. All things being equal, a single proton would generate, the same line width and same height, but obviously one is tall and skinny and the other one is short and fat, and that's already partially an indication of differences in dynamics at whatever sites those two hydrogens are in. And these for the three instructors in this course, extracting dynamic information from NMR spectra is one of our primary research interests. By the end of the course, but more probably 2/3 of the course, hopefully, we'll all be expert in figuring out how this pulse sequence, which has some couple of dozens of pulses, generates this particular three-dimensional spectrum based on moving magnetization around the protein backbone and side chain. So part of the course is to learn how to analyze pulse sequences, and with the hope that you'll at least become a better user of pulse sequences, understand better the methods that you're using in your research, understand better what people in the literature do, but hopefully then be able to adapt whatever latest methods are coming out to your own research. And as I already said, we're ultimately interested in structure and dynamics of biological molecules. A lot of the example spectra that I'll show are for ubiquitin. This is the backbone chain trace of ubiquitin. It's 76 amino acid protein and is used to demonstrate lots of methods in at least solution NMR spectroscopy. What's shown here is Adbax's solution structure of ubiquitin. There's a superposition, well, maybe a dozen structures calculated from NMR data. And of course, if you've seen these before, you recognize in some parts of the core of the protein, the superposition is very tight, suggesting that part of the structure is very well determined. And then you can see here, for example, at the C terminus, the different conformations diverge from each other. And part of that could be dynamics, and part of it could be absence of enough experimental data to constrain the structure. And that'll also kind of be an important part of the course, is figuring out to distinguish those two cases. And then, of course, we'll go on and talk quite a bit in the course about relaxation, both for understanding how that affects sensitivity and resolution in NMR experiments, but also to learn something fundamental about dynamics in biological macromolecules. So with that, this kind of overview in some sense of where we're headed, we can start at the very beginning, and that's that certain nuclei have this property called the intrinsic spin, and it's characterized by a quantum number I. Nuclei with I equal to 0 are inactive in NMR, and all NMR then is done with nuclei with I unequal to 0. As we'll see when we talk about relaxation, nuclei with I equal 1/2 typically are the easiest to use in NMR spectroscopy, and certainly in solution NMR, the large majority of work is done with spin 1/2 nuclei. The one exception probably being deuterium, which is spin 1, but because of its properties has not so bad NMR properties. Unfortunately, carbon 12 is spin 0 and nitrogen 14 is spin 1 with very poor properties for solution NMR. So most solution NMR experiments use the carbon 13 and nitrogen 15 isotopes. And of course, most of the time, as you know, we incorporate these synthetically or biosynthetically into proteins. Particularly nitrogen 15 is present at very low natural abundance. So it's very hard to work natural abundant nitrogen. Now, I didn't want that to happen. We'll see in a slide or two. So what are the properties shown here? So here's the quantum number. As I said, we're most focused on spin 1/2 particles for most of the course. Here's the natural abundance, and if the natural abundance is low, we're generally going to want to isotopically enrich. And then this middle column, gamma, is called the magnetogyric ratio. Unfortunately, I grew up when we called it the gyromagnetic ratio. SI decided it should be magnetogyric ratio, and I'll forget 50% of the time, but those mean the same thing. And this, as you'll see in a couple slides, relates for a given nucleus, the NMR frequency to the size of the magnetic field. And that means larger numbers are bigger. And then you can see right away why hydrogen is a popular nucleus for NMR spectroscopy. It's spin 1/2. It's virtually 100% abundant, and it has the largest magnetogyric ratio shown on this table. And you can see then the problem with nitrogen 15, not only is the natural abundance low, but the absolute value here of the magnetogyric ratio is roughly a factor of 10 lower than for the hydrogen. And that's going to make nitrogen 15 NMR much less sensitive than proton NMR. I don't, from my standpoint, the magnetogyric ratios are just something physicists tell us. I have no idea how you might calculate them theoretically. You obviously, if you know your magnetic field and you measure the precession frequency, you can back calculate what they are, so you can easily measure them. I have no idea how you might calculate them. Anne may know, and you can ask her that question. But for most NMR spectroscopists, these are just some quantities that we're told, and we go on to use them. So then we'll do a very quick introduction to a little bit of the quantum mechanics of spin 1/2 particles, but then switch to the classical Bloch picture, talk about the Bloch equations, and that will take most of today, maybe a little bit of the next lecture. But, so we have a quantum number I, the spin quantum number, and because if the quantum number is not 0, the nucleus has spin, and because it has spin, it has angular momentum. And the magnitude of the angular momentum is given by this equation. So it's h bar times the square root of I times I plus 1, where I is the quantum number. And h bar is Planck's constant divided by 2 pi. I'm going to get pretty tired of writing Planck's constant everywhere. So very quickly, we'll assume Planck's constant is 1 in some units, and you won't see it in the equations. But then if you want to do real calculations, you have to put it back. And you'll see this happen with other quantities as well. We're just going to assume they're unity in some measurement system. And then real calculations, you'll have to add those constants back in whatever units you like. But generally, you can figure out what you need to add by doing units analysis. And that will make your high school chemistry teacher very happy if you can work out units properly. So that's the magnitude. And one of the things that quantum mechanics says, of course, if we have an angular momentum, it looks like a vector. The bowl is supposed to indicate a vector. A vector has three components. And one of the restrictions that comes out of quantum mechanics is that we can only specify the magnitude in one component at the same time. The other two components are made indeterminate by Heisenberg uncertainty principle. And by convention, we pick the Z component to be the other component we can measure. And at the same time, we pick the laboratory frame Z axis to be along the magnetic field of our NMR magnet. So the magnetic field of the NMR magnet is called B0 or B0. And at least in a solution NMR machine, the bore points straight up and down, and the magnetic field goes straight up and down, and that's the Z-axis. So the component along the Z-axis of the angular momentum is h bar times m. M is called the magnetic quantum number, as we'll see from its very close connection to NMR spectroscopy. And m has the property of going from minus I to plus I in unit steps. So if we have a spin 1/2 nucleus, m can only take on the values minus 1/2 or plus 1/2, so that the Z component of the angular momentum is plus or minus h bar over 2. The plus 1/2 state, the state with m equal to plus 1/2, is conventionally called alpha state, and m equals minus 1/2 is conventionally called beta. And then in quantum mechanics, you know that we describe the states with wave functions, which are frequently given the symbol psi. So psi 1/2 means the state where m is plus 1/2, and that'll sometimes be written psi of alpha. And then we'll get tired of writing the psi's and instead switch to what's called Dirac notation. And in Dirac notation, the wave function psi is represented by this bar, some quantum numbers, and then an angle bracket. So psi 1/2 could be the Dirac symbol for 1/2 or the Dirac symbol with alpha, and similarly for the beta state. And one of the convenient things that you'll eventually see about Dirac notation is if we need the complex conjugate of a wave function, we just write the Dirac symbol backwards. So now, if we have an angular momentum, there then is a magnetic moment. And it comes out of quantum mechanics in a way I couldn't possibly prove, that the angular momentum is parallel, that the magnetic moment is parallel to the angular momentum, and the constant of proportionality is this quantity in the magnetogyric ratio. And that means as well that there's a component of the magnetic moment along the Z-axis, and it's given then by gamma h bar m. And finally, if we go ask a friend who's a physicist, what's the energy of a magnetic moment in the presence of a magnetic field, he or she will tell you that the energy is the negative of the dot product between the magnetic moment and the B field. And you have experience with this. If you have two bar magnets, you know that the energy is different, whether they're aligned parallel or anti-parallel to each other. And of course, the dot product would be one when they were parallel and 0 or -1 when they were anti-parallel. If you look back, I should have pointed out, since I said we're interested in units analysis, look at the units of gamma. The units of gamma are Tesla, 1/Tesla times seconds, the reciprocal of Tesla times seconds. So when we come here and ask about the energies, over here, energy is going to be something like joules. The magnetic field we could measure in Tesla. Gamma is Tesla per second. And what we end up, and then if we do this, for example, for the E field, do the same thing. Here, the Z and B naught are parallel to each other, so the dot product is just 1. We end up clustering gamma and B naught together and call minus gamma B naught omega naught. So what are the units on omega naught? Gamma was 1/Tesla seconds times Tesla is 1/seconds. Seconds look like a frequency. 1/seconds looks like a frequency. Omega naught is a frequency. What are the units of H bar? H bar has units of joules times seconds. So joules times seconds times the frequency is joules, which properly is an energy. M is just an integer, it doesn't have any units. So far the units work out. This minus sign is kind of unfortunate. That's just the way it is. That means if gamma is positive, the frequencies are negative, and hydrogen, carbon-13 all have positive gammas and therefore negative frequencies. A friend of ours, Dan Raleigh, you should just teach NMR using N15 as your example, because it has negative gamma and therefore the frequencies are positive and it would be much less confusing to students, but so be it. Okay, so if we put some spins into our magnetic field, the dot product between the field along the z-axis and the magnetic moment is just the product of the B naught field times the z projection of the magnetic moment. And we know the z projection of the magnetic moment. So here then is the energy of the alpha state. And here is the energy of the beta state. And I've drawn them here. You have to remember, if gamma is positive, omega is negative, so alpha has lower energy than beta for positive gamma, even though this minus sign here might make you think that should be the lower energy. It's the higher energy because gamma is negative if we're talking about hydrogens. And that's the source of the confusion. And you can see right away, right, the energy difference between the two energy levels is H bar omega naught, and that means the energy difference is proportional to the size of the magnet that we have. And that's extremely critical for NMR spectroscopy. The larger the energy gap, the better, and that simple fact drives the development. One of the things that drives the development of bigger and bigger magnets all the time. They're just increasing this energy gap. Of course, if we have now a collection of spins at equilibrium, some will be in the alpha state and some will be in the beta state. And what equation determines how many are in each state? The Boltzmann equation. So we can immediately write that down. So here's the Boltzmann equation, that the population of a state with some value of m is the number in that state divided by the total number. And here's the Boltzmann equation. Now, one of the first problems that you'll do will be, how large of energies are we talking about? And it turns out that the energies associated with the magnetic moment of the nuclear spins under typical solution conditions are much less than kT. They're very small energies. And as a result, these exponentials can be expanded in first order and Taylor series without any loss of accuracy. Things could be different for very high polarization at very low temperatures, but that's a problem for Ann to talk to you about, not me, or Malcolm Levitt. So if we expand in Taylor series, then we can easily do the sum, or at least Mathematica can do the sum for us. So we have the populations here as now a function of the B naught field and gamma. Oops. And again, you see right away another reason for preferring large gammas and large B naught fields, because those are going to generate larger population differences between the two states. And all spectroscopy, not just NMR, basically the sensitivity depends on the population difference between the states that you're doing spectroscopy on. So these turn out, if we put m equal a half here, B naught, something like 11 Tesla, and gamma for protons, this factor turns out to be something like, for the more populated state, is something like a half plus 10 to the minus fifth, and lower population is a half minus 10 to the minus fifth. So we have very small population differences, which is why NMR is insensitive. Again, why we want bigger magnets. That situation is very different, for example, in fluorescence spectroscopy. You're doing optical frequencies. The energy differences are so large that the upper state basically has no population at all. And the system can be treated as everything in the lower energy state, whereas NMR is completely the other extreme. So each spin has a certain projection of magnetic moment onto the z-axis, and we have a large collection of spins. So if there's more population in one state than the other, then if we add up all the z components, some of them are positive, some of them are negative. If they don't exactly balance, there's going to be some net magnetization. Right? So the net magnetization is the population weighted sum of the different M states. So we again can calculate what the net magnetization is of a sample. So now we have some number of spins in each state. We want to do the sum. Again, we need to weight by the populations. We again expand in Taylor series. And again, we ask Mathematica to do the computation of the sums. Shown here. And again, you can see this strong dependence on B naught and even stronger dependence now, quadratic dependence on gamma. Again, why we prefer large gammas. Now, this is then the magnetization one expects at Boltzmann equilibrium. Of course, if you put a sample into the magnet, after it's been sitting on the lab bench for a while, it's at Boltzmann equilibrium in the Earth's magnetic field, and you put it into the magnet, it's not at Boltzmann equilibrium in the presence of a 14 Tesla magnetic field. You expect eventually it'll come to Boltzmann equilibrium. The people who have done some NMR, what process determines how long it takes to come to Boltzmann equilibrium when you put the sample into the magnet? T1. And fortunately, for most of the samples that you work with, T1 is likely to be order a second. So by the time after you put the sample in the magnet, by the time you get done drinking coffee and shimming, you're at Boltzmann equilibrium and you can start your experiment. However, a very famous case of the Dutch physicist Gorter, who tried to do an NMR experiment, but he unfortunately picked a sample with an extremely long T1 and basically never got enough polarization to do the experiment. I've also so far kind of talked as if I'm thinking about individual spins. And generally, I'll try to avoid talking about what individual spins are doing. And again, you can ask Ann questions about that when she's lecturing. But a typical solution NMR sample has 10 to the 17th or so spins in it. And I can pretend in a Gedanken experiment that I can divide those 10 to the 17th spins into a bunch of sub-ensembles, where within each sub-ensemble, those spins behave the same, and I can just sum up their properties to have some magnetic property for the sub-ensemble, and then average over all the sub-ensembles to find out what the bulk is doing. If I have 10 to the 17th spins, I can say, I want my sub-ensembles each to have 1 million spins, and I still have 10 to the 11th sub-ensembles. So as long as we're talking about normal solution experiments, this is a perfectly fine approximation, and it avoids me having to think too carefully about the weird quantum mechanics of the single spin. If you want to go off and do single spin EPR, you have to worry about these things. But single spin NMR is probably past my career before we have to worry about it. So if I make a mistake and start to talk as if I'm thinking of an individual spin, that's just a grammatical mistake. I'm always thinking about these sub-ensembles where there's some net magnetization in the sub-ensemble. I'm wondering about its properties. So for spin 1/2, then we can specialize those equations. Here's the population. Here's the net magnetization. The picture is shown here. There's a tiny reduction in population in the upper state, gain in population in the lower state. Delta E between the states is minus h bar times omega naught. And this picture looks fairly similar, right, to a picture you might draw for optical spectroscopy, except they're talking about very different kinds of energies. We could, and some of the earliest attempts to measure NMR were done basically by irradiating the system with a magnetic field of the right frequency to match these energy levels, essentially doing the same kind of absorption experiment that you might do on a UV vis machine on a benchtop in a laboratory. But because the population difference is so small, that turns out to be a very difficult way to do NMR spectroscopy. And eventually, people figured out much better ways, what we now call pulse Fourier transform NMR. In fact, the way we now do NMR with pulses and then measuring the free induction decay is so overwhelmingly popular that we think of that as the NMR experiment, as opposed to thinking somehow of an absorption experiment being the fundamental experiment. Back when pulse Fourier transform NMR was invented, people wrote papers about how good an approximation was the pulse Fourier transform spectrum to the conventional way of measuring NMR. But these days we mostly don't care about that at all. This is the NMR spectrum. And that means rather than thinking about absorption, we're going to think most of the time about what does the magnetization do? How does the magnetization evolve? And again, we can go ask our best friend in the physics department, given some net magnetization that I've created by putting the sample into a very strong magnetic field, how does that magnetization evolve in time? And your friend will tell you that the evolution of magnetization is given by this equation, that the time derivative of the magnetization, or the net magnetic moment, is given by this cross product between the magnetization and the magnetic field scaled by this constant gamma. And of course, remember, minus gamma B is what we call a frequency. This equation says that the magnetization precesses around the instantaneous magnetic field. So spins aren't very smart. They basically know how to do one thing. Their net magnetization precesses around the field. And what does precess mean? Pardon? Well, a little more specific than that.
Something that rotates around something else that rotates.
So precession is rotating around an axis at fixed angle. So if you haven't played with a top when you were a child, actually I still play with them, and you spin a top, right? Unless it's perfectly vertical, if it's tilted, you see that it slowly rotates. I mean, there's the fast spinning that generates the angular momentum, but there's the slow rotation. And if you watch, that slow rotation stays basically at a fixed angle relative to the Earth's gravitational field until friction slows it all down and it falls over. So it's the same thing here. The magnetization will precess at fixed angle relative to the B field. And if we change the B field direction or magnitude, then the magnetization just precesses with respect to the new field. There's Faraday's law says that if you have a time varying magnetic flux through a circuit, you generate an electromotive force, and that can be amplified and displayed on a computer screen. So the basic of an NMR experiment is there's some precessing magnetization. We have a coil of wire nearby and what's called the NMR probe. The precessing magnetization, as it sweeps past the coil, generates an EMF. We amplify it, and that's our free induction decay. So a pretty simple experiment. Here's an example of precession. Red is the magnetic field, blue is the magnetization. And you can see the magnetization just rotates around at fixed angle. And if the direction of the magnetic field changes, there's just a new angle. if we had some complicated time-dependent magnetic field, computationally, we would just divide the time-varying magnetic field into small steps where the field could be regarded as constant. Let the magnetization process around that fixed magnetic field for a short time interval, then jump the magnetic field to the new position, process. And if we made the time steps narrow enough, that would approach the exact result for any complicated magnetic field. And that's in fact how most calculation programs work. Just divide things up into small enough time steps that you can treat the magnetic field, the red magnetic field, as constant for a short time interval. Now the difficulty with this experiment is we have the sample at equilibrium. The magnetization is along the B naught field. So the two are parallel to each other or anti-parallel to each other. But what's the cross product of two parallel vectors? 0. So we can't put a coil of wire near our sample at equilibrium and see anything. Actually, we can see a small jittery noise called spin noise that Alexei Gershow works on at NYU. But from our standpoint, we don't see anything at all because the magnetization is parallel to the B naught field. So to see anything, we have to get the magnetization to be non-parallel to the B naught field. One thing you could do is quickly tip the magnet on its side, but you can only do that experiment once in your career. You could rapidly take the sample out and move it to a new magnet with a different orientation of the field. And that's actually done for some neutron experiments where you have a flux of neutrons going through a magnet with the field oriented in one direction. The neutrons get polarized, and then they continue on to a magnet with the magnetic field in an orthogonal direction, and now they start to process. The only difficulty there, right? If you want a new experiment, you have to build a new set of magnets. So it's not so convenient.
Can you flip the sample inside the magnet without taking it out?
Well, then it would still just be anti-parallel. So the cross product is still
90 degrees.
so the a little bit of complication with that. So, since you're not going to do it, let's forget about it. I mean, there are experiments where people change the orientation.
In solid state,
Yeah.
flip angle.
Right, but let's leave that for Anne. And if we work this out, clearly, if we don't want to tip the magnet, we have to generate a second magnetic field. And it turns out if we do some more math than we're going to do, is that we need a field that's polarized orthogonally to our main field. And it has to have a frequency somewhat close to omega naught. That a frequency very far from omega naught won't be effective. That's basically because, again, the spins only process around the magnetic field. So if we have two fields, one orthogonal to the main field, then what the spins will process around is the vector sum of the two. So we have 11 Tesla field for protons. That's a field equivalent to 500 megahertz. And now we want to turn on a field that's orthogonal. On a solution probe, because of heating and other kinds of issues, you're more or less limited to a field strength measured in hertz of, say, 100 kilohertz. So your 500 megahertz to 100 kilohertz, and your 5,000 times smaller field in the XY direction than the Z axis. The vector sum of those two fields is essentially on the Z axis. So if we just turned on a CW field orthogonal to the main field, the vector sum is so close to zero, we don't see any precession. It's, I don't know, thousandths of a degree difference between the two. And our experiment depends on how much we get into the transverse plane. So that doesn't work. We just can't turn on a strong enough field in the X or Y direction that's CW. And the trick is something magical happens if the field is close to resonance, if the field is modulated in time to be close to the Larmor frequency, or conversely, to be close to having an energy that's matched to the energy difference between, say, the alpha and beta state. That's what we all said. We're going to turn it on, blah, blah, blah. And so why do we have to be resonant? I'm just going to show a simple little demonstration. How many people have pushed a child or a friend on a swing at the playground? Everybody has. Right? They start at rest, you give them a push, they swing away, they come back, and you give them another push. But you have to push them in synchrony, right? If you push them out of synchrony, then they come back and your push stops them. And then if they're a child, they start to cry. So you already know if you're trying to push someone out of swing, that you have to do something synchronously with the period of the swing. Otherwise, nothing happens. But you could imagine another way of doing it. Rather than waiting for a full cycle, you could give a little push, run around to the other side, meet the swing at just the right moment, give it a push back the other direction, run around, give it a push. And even if you gave little tiny pushes, eventually there would be a large amplitude of swinging, as long as you were synchronous with the period of the swing. So that's what you're going to see. We're going to turn on a CW field. It's very tiny, pointing along, say, the plus x-axis. There's a small tilt angle. The magnetization will rotate around that tilt angle, but it won't get very far from the z-axis. But we're going to meet it on the other side and now have a minus x magnetic field, a new vector sum, and the magnetization will start to process around that new field. And we run around and meet it on the first side again. And you'll see what happens. If I can get this to run. So blue is the magnetic field. You can see it's just moving back and forth, always close to the z-axis. But the amplitude of motion of the magnetization keeps getting further and further away from the z-axis. Because every push is synchronous to add a little bit more deflection from the z-axis. And if we wait long enough, just like giving small taps on the swing, the swing eventually will have large amplitude. Here we can get the magnetization very far from the z-axis. So I've imagined just turning on a weak square pulse back and forth plus x minus x. That turns out, first of all, to be very difficult to do. It's very hard to turn a magnetic field on in a coil, which comes from switching current in a coil, positive and negative, very fast. First of all, that's very difficult to do in reality. But also it turns out that if we looked at the math, the only effective part of this are the sinusoidal components of the square wave anyhow. So it's enough just to cosine modulate the magnetic field. And if we cosine modulate it at the right frequency, close to the Larmor frequency, we get this effect that a weak field, but because it's resonant, can generate large deflections of the magnetization away from the z-axis. Now, the other aspect of this, and I may have better pictures later on, is this depends. What we would like to do is bring all the Z magnetization, say, down to the x-axis. And that requires, what we don't want to have happen is have the z-axis be spread all around the xy plane. Because if we took the Z magnetization and just spread it in the xy plane, there's magnetization orthogonal to the z-axis. My little sub-ensembles, each sub-ensemble may well be precessing around the z-axis, but the net sum seen by the coil is going to be zero, because every bit of magnetization pointing along the plus x-axis is going to be canceled by magnetization on the minus x-axis. If we did that, we would say the system was saturated, and a saturated system doesn't generate any signal. So it's not enough to bring the magnetization to the transverse plane. This has to be brought to the transverse plane with basically the same orientation when summed over the sample, or the volume of the sample seen by the detector. And that depends on a property that the radio frequency field, the magnetic field that we turn on that we call the pulse, that's cosine modulated at something near the Larmor frequency, that field has to be phase coherent over the volume of the sample. So if you turn on a so-called X phase pulse, the radio frequency pulse seen in the middle of the sample has to have X phase. What the spins at the top of the sample see has to be X phase. What the spins at the bottom of the sample see has to be X phase. If that wasn't the case, if there was some kind of phase dispersion along the sample, then the sum would be certainly reduced, if not going to zero. If you had essentially plus X phase at the top of the sample and minus X phase at the bottom of the sample, those two bits of magnetization would end up canceling each other. So a really important part of the experiment is that the radio frequency that's generated by the NMR machine has to be phase coherent over a macroscopic volume. And it turns out that's easy to do in RF frequencies. It's really hard to do at optical frequencies. That's why simple things that are very simple to do by NMR spectroscopy can be quite hard to do at optical frequencies. And you have to have very fancy lasers and all kinds of stuff to get even very simple experiments to work, because of how difficult it is to get phase coherent optical pulses compared to phase coherent radio frequency pulses. But the whole thing depends on this property. The whole experiment depends on the property that the RF pulse, or the RF irradiation, is phase coherent to a high degree across the macroscopic sample.
If there is a phase problem, would it end up showing in only lower intensity or the broadening of line at the same time? If we have a phase RF problem.
So you would, well, if you did pulse then acquired, you would just see loss of intensity because you turn the pulse off and the line width is in the absence of the pulse.
Okay, so
but when a probe is characterized, there'll be an experiment called a mutation experiment where you have Z magnetization, you turn on the field and just rotate the Z magnetization and then ask how much of the original Z magnetization is left after I've turned it on for, say, 720 degree rotation. And the more phase coherent the RF, the more of that magnetization will be left.
So this so-called B1 inhomogeneity that we measured, is it just the
Yeah.
phase or the amplitude?
It can be both, but in my picture here, talking about the importance of phase coherence, I'm not worried about the amplitude, but in the practical sense, both contribute. But later on, when we talk about coherence in NMR and what it is, that coherence basically gets created because of the phase coherence of the RF field. So with this little bit of talking around the problem, we want to generate a sinusoidally modulated field. It's conventional to write it as a cosine wave with some frequency omega RF that's going to be close to the Larmor frequencies, omega naught. Omega naught, by the way, is called the Larmor frequency. That field may have some phase. So when we talk about X phase pulses, Y phase pulses, that refers to this phi. And it has some amplitude. And you'll see why in a moment why we have this factor of 2 here. It's a magnetic field. So we could measure B1 in Tesla, but we don't. Normally we measure it in frequency units because gamma times B1 is a frequency. That'll be the frequency of rotation of the magnetization during the pulse. That sometimes is called the Rabi frequency. So it's easy to get confused because we have the actual frequency of the modulation, that's omega RF, and we have the amplitude of the field, which here is called B1, but more commonly would be called omega 1 because we think of it as multiplied by gamma. So you have two things that look like frequencies, and only one of them is a frequency. The other one is a measure of amplitude in peculiar units, but it's convenient. Otherwise, we would be talking about microtesla all the time, which would be inconvenient. A linearly polarized field like this can always be decomposed into two circularly polarized fields rotating in opposite directions. And it turns out for the NMR experiment, one of those is useful. Remember, we're chasing the magnetization, like running around the swing. And here we have to run in the same direction as the magnetization is processing. And the magnetic field going in the other direction isn't useful, the so-called counter-rotating field. So this gets dropped, which is why we have this factor of 2. So the useful part of the field is the circularly polarized field in the productive direction. Of course, we don't know what that direction is. I was told once by Mark Rance that when he was in Richard Ernst's group and Richard Ernst was writing his famous book, there were all kinds of discussions amongst the postdocs as to which direction the nuclear spin magnetization actually rotated. And every time somebody thought they had a proof, Alexander Volkan would disprove them. So we adopt a right-handed convention, basically following Ernst. So we'll pretend positive rotations are right-handed, but that's just a convention, and all the math works equally well if we assume the other left-handed rotation. And if you go back to the early days of NMR, people chose one convention or the other. So if you read old papers, you have to make sure you understand which convention is being used. So once again, the spins only really know about the vector sum of our two fields. And now it's also useful to switch into a frame that's rotating at the same frequency as the RF frequency. We'll do this more formally later on. Right now, I'm just kind of telling you some results that in a frame rotating at omega RF, the B1 field looks stationary. We're chasing the B1 field at its frequency. It looks stationary to us, and it has the effect that the B0 field appears to be scaled down. So this is called a reduced static field. And then capital omega here is the difference between omega naught and the frequency of the B1 field. So if we match them exactly, we would say we're on resonance. And then the B0 field in the rotating frame would look to be 0, in which case the magnetization wouldn't precess in that rotating frame. It would look stationary in the rotating frame, even though in the laboratory frame it's spinning around at the frequency omega naught. In the rotating frame, it would look stationary. Here's just some examples. Here's a 1 megahertz NMR spectrometer, and I've now turned on the RF field, and I'm looking in the laboratory frame. The magnetization starts to precess away from the z-axis, and eventually it hits the transverse plane, and I turn off the field and I say I've done a 90-degree pulse. So during the 90-degree pulse, that magnetization is precessing, but it ends up in the transverse plane. If I switch into a rotating frame, now I switched into a rotating frame that's 0.2 megahertz off resonance in my 1 megahertz NMR spectrometer. I do the same experiment. In the rotating frame, I still see precession before I hit the transverse plane. But you can see that apparent precession frequency is much slower. And it's because in the rotating frame, I see the scaled magnetic field, the difference between the RF field and omega naught. And if I switch to being on resonance, then I just see the simple behavior where the magnetization just seems to rotate from Z straight down to the transverse plane with no precession, because in the rotating frame, I'm on resonance. And it's a little tricky. It takes some time to get used to the rotating frame. Eventually, you forget it's confusing and just get used to thinking about it. You can always blame your parents. You didn't have enough pops and things that rotated when you were a child. Too many things that went in straight lines when you played with them. The spectrometer actually is built as if it's in the rotating frame. So that's actually very convenient. There's times where we want to switch back to the laboratory frame and think about relaxation processes. But the way the spectrometer works, it acts like it's in the rotating frame. Yep.
What is the 0 magnetism?
That means that's how far off resonance I am. So now I'm sitting right on resonance. So in the rotating frame, the effect of precession seems to have gone away. There's just this rotation around the stationary B1 field. Again, language that we'll see over and over again in the rotating frame. Instead of talking about the B1 field, I'll almost always talk about the resonance offset, capital omega, the difference between the Larmor frequency and the frequency of the RF field. In that frame, in that rotating frame, the B1 field will be stationary, and the phase of the B1 field in the transverse plane turns out to be the same phase as in that cosine wave. So if the phase and the cosine wave was 0, then the B1 field just points along the x-axis, and we would say that's an x field, so on and so forth. Now, everything in the NMR experiment, by the way, is rotationally symmetric around the z-axis. So what we call x or y is completely arbitrary. It's just that if we pick some direction relative to the coil to be x, orthogonal to that is y. But the actual position is, it doesn't matter. And if you've collected an NMR spectrum, you know that you can apply an arbitrary zero order phase and it doesn't do, it doesn't harm the spectrum. Zero order phase is just rotating around Z. And typically we would do that to get whatever the real axes were in the probe to align with our mathematical axes when we process the spectrum. So that's arbitrary, and then this is 90 degrees. The vector sum of B0 and B1, of course, is critical for what the magnetization will process around. The vector sum is called the effective field in either magnetic field units or these pretend frequency units. And then the B1, the orientation of this field depends on the phase and on what's called the tilt angle theta. And the tilt angle theta is defined here, the amplitude of the B1 field divided by the amplitude of the offset and then the arctangent. And here are just some more pictures of what this looks like. I turn on some B1 field. I have an effective field, and the magnetization will process around that effective field while I have the B1 field turned on. If I'm on resonance, the B1 field just points along some axis in the transverse plane, and then precession means processing around the disk, orthogonal to that field. The magnetization rotates around the field at a frequency then that is gamma times the magnitude of the field, and frequency times time is an angle. So if we have an effective frequency omega E and we turn on the RF for some time tau P, we'll end up with some rotation angle alpha. And if we were on resonance, we would just have omega 1 times tau P would be an angle alpha. So frequency times time is always an angle. And again, here are just more pictures of what this looks like. Here is on resonance. I turned on a B1 field in this direction. Magnetization rotates into the transverse plane. If I'm a little off resonance, there's some precession. So the magnetization starts to precess as it rotates down from the Z-axis towards the transverse plane. After this pulse, if I turn on the NMR receiver and record a spectrum, what's going to be wrong with the spectrum?
Phase.
It's going to have a phase error. The magnetization that I wanted to end up on X ended up rotated a little bit away from X. And I'm going to see a phase error in the spectrum that then I would try to mathematically correct.
Is this phase then will be a correctable phase or dispersive?
Well, eventually, see, the effect of the phase angle is going to look like it mixes in part of the dispersive signal. And here, it would be easy to correct because it's just one spin. But of course, if you have different spins, they all have different offsets, so they all have a different phase error. And if the phase aren't too large, they're linear with offset, and then you do a first order phase correction. Anyhow, that's all for the future. Just to go back to something we already kind of talked about, right? We start here at Boltzmann equilibrium. After a 90-degree pulse, all the magnetization is in the transverse plane. That means if there's no Z magnetization, the population difference must be 0 between the upper and lower states. But again, that's different from saturated. If the system was saturated, there also would be no population difference between the upper and lower states, but there wouldn't be any transverse magnetization either. Whatever transverse magnetization there is would have been dephased in the plane, so there was no net transverse magnetization. And then something we can easily do in NMR, as I said, is hard to do at optical frequencies, is because the system is phase coherent, we can invert the populations with 180-degree pulse. So the experiment, turn on the RF field, rotate the magnetization into the transverse plane, turn off the RF field. Now the magnetization processes around the B0 field. I have a coil and I measure an electromotive force. That's my signal. All great, but that can't go on forever. If the processing magnetization processed forever, I wouldn't display the EMF on a computer screen. I would sell it to the power company. So eventually the system has to come back to Boltzmann equilibrium. And in the very beginning, Bloch said there were two simple mechanisms for coming back to Boltzmann equilibrium. And he called the first one R1, or its reciprocal T1, and that restores Boltzmann equilibrium to along the z-axis. And the other process is T2, or R2, and that's dephasing of any transverse magnetization. And in macromolecules, those two rate constants can be very different from each other. In small molecules, they might be close to identical, but in macromolecules, R2 can be much, much shorter than R1, or much, much larger than R1. T2 can be much shorter than T1. So that means here that if we generate transverse magnetization, and now it's processing doing its thing, it can dephase in the transverse plane so that there's no longer any net transverse magnetization so fast that we still don't have any recovered Z magnetization. So we can get to this saturated state where there's no net transverse magnetization, there's no net Z magnetization yet, and then we have to wait for some multiple of T1 for the eventual recovery back to Boltzmann equilibrium. And again, you can have NMR systems where T2s could be less than milliseconds or on the order of milliseconds, and T1s could be on the order of minutes or longer. But you have to wait an extremely long time between repetitions of the experiment, which also kind of harmed early efforts. Mm-hmm.
I understand calling them longitudinal and transverse, but what's the origin of the term spin and spin lattice?
So spin lattice, so remember here, suppose we're in the saturated state, and now we want to have to go back to Boltzmann equilibrium. Well, here, then some of these beta spins are going to have to go down to the alpha state. And that means the system is going to give up some energy. Where does that energy go? It goes to the other degrees of freedom of the molecule. Tumbling of the molecule, collisions with water, all sorts of other things that eventually are thermal. And historically in NMR, all these other degrees of freedom were called the lattice. So spin lattice means we're going to have to exchange energy with the lattice, with the surroundings. Spin is sort of sillier name. I don't even know where it comes from, but it just refers to the dephasing of the transverse magnetization. And everything I don't know, I pretend you can ask Ann. So these are the simple equations that you wrote down. First order differential equations for recovery to equilibrium and dephasing of X or Y magnetization. Here's solutions of the differential equations. Transverse magnetization decays away to 0. with a time constant T2. Longitudinal magnetization recovers to Boltzmann equilibrium with a time constant T1. And that's probably for today a good place to stop. What comes next to finish out the Bloch equations is then just to add precession equation with the Bloch equation, these decay equations. So then we have a set of equations that describe the coupling of precession and relaxation back to Boltzmann equilibrium. Those equations are called the Bloch equations, and they're the complete description for a single isolated spin. But of course, we're not interested in single isolated spins. We want to know about multi-spin systems, and much of the next development of theory after the Bloch equations is to try to recast a theory that is general enough to describe all the cases we're interested in, but formulated in a way that looks as much as possible like the Bloch equations, because we have a much more intuitive sense of how the Bloch equations behave than complicated quantum mechanical equations. So tomorrow we'll finish off this lecture. I'll try to figure out how to get everybody access to the Dropbox so you have a copy of the lectures going forward. If there aren't any questions, I'll see you tomorrow.
Hi,
Hello.
just a quick question. So I'm auditing.
What?
I was just wondering if it's possible for me to get the Zoom link. I can only come in for Wednesday. I've Zoomed with you before. Can I just send you my email?
Send an email. Have you already emailed her?
No.
So then email me and I'll send you Whitney's, because she's handling all the communication for the folks.
Okay, that's perfect. Thank you. And would we also be able to get onto the Dropbox as well?
Yes.
All right, thanks.
That's what I have to get arranged.
Thank
If it
you.
was all Columbia people, it's easy. Yep.
Hi, I'm Alan. I just want to introduce myself, Alan.
Ah, okay.
Starts. So I'm auditing the class,
Mhm.
and I'm just trying to, this is, I'll be honest with you, very complicated. I'm just trying to just basically glean as much as I can for my own research. So I'm just beginning to operate the console here, just to kind of like get a spectrum of my apo protein. And so just starting from there, and hopefully, using it to, look at some protein interactions and the chemical shifts that are produced. So anyway,
That's perfect.
I don't know how long. I have two other courses, and this is my second year. I have my bioinformatics course this semester, and my molecular biophysics. So I'm gonna try and stick with this depending on how loaded things will be. But I will try to